Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series for the BSc Honours Physics students. We have been going through a set of lectures on diffraction, a phenomenon which could be again explained only on the basis of wave theory of light, similar to what we have done in the case of interference. In the last lecture, we have been seeing the basic features regarding diffraction, the definition of diffraction, etc. As far as this lecture is concerned, the contents will be Huygens' construction of a spherical wavefront, rectilinear propagation of light, half-period zones, and the resultant amplitude. In the last lecture, we saw how from a point source which I have got here at S, the PQR is the primary spherical wavefront, and after time t, how does it advance? Or in other words, we are trying to explain the propagation of light in space. From PQR, it goes to P prime, Q prime, R prime, and it goes on like that. They are the so-called spherical wavefronts. In this lecture, where the main purpose will be to explain the rectilinear propagation of light, from spherical wavefront, we will go to plane wavefront. What do you mean by plane wavefront? You have got a spherical wavefront. If at infinite distance, or if you take a spherical wavefront which is very large, a spherical wavefront is very large, or you go to a large distance, the curvature you have got here, it keeps on changing, and ultimately from a spherical wavefront, a part of the spherical wavefront can be considered as a plane wavefront. You have a very large sphere, the radius of curvature is very large, a part of a large curvature will be a plane wavefront. So, you take a portion here, this is a plane wavefront. You understand a point here. You have infinitely large thing area, and a part of it you see here you got a straight line. So, this region will be a plane wavefront. Okay. I will come to the plane wavefront a bit later. Now, we are trying to explain the rectilinear propagation of light. What do you mean by rectilinear propagation of light? In other words, it means the formation of shadows ought to be explained. As I told you in the last lecture itself, the formation of shadows or the dark regions could have been easily explained if we were convinced about the Newton's ray concept. If Newton's theory could have been applied or used to explain the formation of images, it would have been much easier. But having talked about diffraction, that is bending of light beam around obstacles, then you ask the question naturally, will it not be a source of light to be seen in the shadow region also, because the light beam is bending around the obstacle. There will be light falling in the shadow region also. So, the bending of light around the edges of an obstacle or the appearance of light within the geometrical shadow, it is known as diffraction. There will be light within the geometrical shadow. If there is going to be light within the geometrical shadow, then why do you say a shadow is formed, or how will you explain the darkness in the shadow region? You have the shadow or the shadow formed, and how will you explain the shadow? According to Fresnel, if wavefront can be divided into a larger number of stripes or zones called Fresnel zones of small area, and the resultant effect at any point will depend on the combined effect of all the secondary waves emanating from various zones. So, the point number 1 is a spherical wavefront we are talking about. From that you go to a plane wavefront. I will show a plane wavefront. The plane wavefront will be divided into number of strips or zones. You will have zones. They are called half period zones. I will tell you why they are called half period zones. Then the light coming from the half period zones will give rise to some intensity, and the resultant intensity that you are going to get from the light coming from all the half period zones ought to be calculated. Now, therefore, the source is here and the light wave will be coming here. You will have a primary wavefront, and here at a large distance you will be having from a spherical wavefront that you will be having here, you will have a plane wavefront. According to Fresnel, a wavefront can be divided into a large number of strips or zones. That is what I told you just now. They are the Fresnel zones of small area, and the resultant effect at any point will depend on the combined effect of all the secondary waves emanating from various zones. So, what I am going to tell you now, without having so much of time being spent on explaining, this is the primary wavefront. From the spherical wavefront, you consider primary wavefront. They are the so-called half period zones. That is what was done by Fresnel. Now, principally what we are doing in this lecture is to advance or to understand the Fresnel's theory, which was put forward by Fresnel to explain the formation of shadows. So, these zones that we are talking about are called this is the first Fresnel zone, this is the second Fresnel zone, the third Fresnel zone. I will come into the details a little later. So, let me now go back to the rectilinear propagation of light. If an opaque obstacle is placed in the path of the light beam, a sharp shadow is cast on the screen, indicating thereby light travels in straight lines. Because as I told you, you have a sharp obstacle, then the shadow is cast. The shadow being cast can be explained assuming that light is traveling in the form of straight lines. But on the contrary, that is what Newton said. But on the contrary, you are now talking about bending of the light beam. So, because this is what you will be having here. You have got a light source, you put a sphere here, place a sphere, you get an image, and this is the shadow that has been cast. The shadow is obviously dark. If I now say the light that is coming here will be falling at the edges, the light will be bending. You know, when the teacher is coming, even if the teacher doesn't see the people who are making so much noise in the class, or as is being done normally, that that students are talking or they are beating drums, the sound coming is being listened by the teacher who is far away from the students. He is not in contact, direct sight with the students, but still he is able to hear because sound wave is bent. Similarly, if light wave is bent, then what will happen is the light source is coming, light is bending here also, from this also edge also light will be bending, there will be light falling here. So, what happened to the light? You are seeing only darkness, that is what you naturally see. If you assume light to be bent around the edges, that is called diffraction. Then obvious question is, well, then what happened to the light here? That should be, I should see light here, I don't see light, I have a shadow, Now, how to explain the formation of shadow or how to explain the darkness that is found here is the question before us. That was what was done by Fresnel. Fresnel was able to explain, in spite of the fact that the light beams bend. The light waves bend around the edges of the obstacle. In spite of it, there is a darkness, and so he proposed a theory that is considering the half period zones, destructive, constructive, and half period means what? T by 2. T by 2 means what? The path difference between the two zones will be lambda by 2. One will be constructive, the other will be destructive, constructive. Therefore, the resultant will be 0. Finally, what I am going to show is the resultant intensity. Even though the light beams bend, the intensity of light that is being obtained here will be negligibly small. So, the essence of the lecture, this lecture and the next lecture, the final result will be the following. Light beams do bend, diffraction is there. In spite of the fact that light beam bends, diffraction is there, the intensity that is obtained here is going to be extremely small. That is the reason why it appears to be dark. How would we say that the intensity is small? Because I divide the plane through which light is passing, the plane wavefront, into off period zones. There will be some of the zones will be giving rise to light amplitude with a plus sign, some will be minus sign, because T by 2, the phase difference will be there between the light coming through various zones by lambda by 2. So, the amplitude will be positive, amplitude will be negative, positive, and from the light coming from various zones, the amplitudes will be opposing each other. That is the reason why the resultant amplitude here will be small. Because the resultant amplitude is small, intensity is small, so you get darkness. That is what I am going to show finally. So, now I pass on to what is called, you have a person standing, you have the shadow here. Now, even though light bends, but as I told you, the intensity that you have here is almost 0. That is the reason why it appears to be dark. So, its light spreads to some extent into the region of geometrical shadow because of the bending of the beam, as I told you, around the edges of an opaque obstacle. But the intensity of light inside the shadow is extremely small, as I told you just now, and hence it looks as if light travels in straight lines. Now, the problem is to explain the rectilinear propagation of light, or in other words, the problem that we have to understand or to explain is how the intensity becomes almost 0. This is done using the plane wave front. The ABCD is a plane wave front perpendicular to the plane of the paper. So, you got the paper here. So, you got the light is coming from the source. We talked about spherical wavefronts. A part of the spherical wavefront will be a plane wavefront. So, ABCD is a plane wavefront, and that is to find the resultant intensity at P due to the wavefront ABCD. Fresnel's method consists of dividing the wavefront into number of half period elements or zones called Fresnel's zones, and to find the effect of all the zones at a point P. They are called half period elements because the path difference between one zone, the other zone, the successive zone will differ by a path lambda by 2. So, with here is the source, right? The P is the light source, or you can have the other way around. P is the point at which you want to find the intensity, the final intensity. The light is coming from here. The arrow shows the light coming from this direction. When the light is far off from this region, this wavefront, instead of that being considered a spherical wavefront, it can be considered as a plane wavefront. A part of the spherical wavefront will be a plane wavefront. What I now do is, you take this region here, you take the point O, from O you draw a line to the point P. What is the point P? P is the point where I want to find the resultant intensity of what? Resultant intensity of light coming from the plane wavefront ABCD. So, I divide this ABCD into number of half period zones. What is the first half period zone? From O as the center and P is the point here, I draw a perpendicular. Then with PM1 or OM1 as the radius, you draw a circle that gives what is called the first half period zone. This is your B. B maybe OP is the distance from O to P, OP, that is equal to B. So you have your the OM1 is the first half period zone. Now take this distance here from P to M1, let that be B plus lambda by 2. So with B plus lambda by 2 as the radius, draw the circle, then B plus 2 lambda by 2, that is B plus lambda, you draw a second circle, and so construct number of half period zones. Let us have a break at this point and we will see the rest at the break. Welcome back at the break. We have been talking about the construction of the so-called half period zones in the wavefront ABCD. ABCD, the plane wavefront. I have the first half period zone that you have got here from O to P. P is the point, that is the important point. That is P is the point where I want to find the intensity of the light finally produced from the light coming from the first half period zone, the second half period zone, third half period zone. Now they are called half period zones because what is the difference between M1 and M2? M1, you got M1 here, PM1, the length of this is B plus lambda by 2. What is PM2? You look at M2 here, PM2. PM2 is, what is magnitude of PM2? That is B plus 2 into lambda by 2. That is 2 and 2 will be getting cancelled, B plus lambda. So you got lambda by 2 and here you got lambda. So between this zone and this zone, there is a path difference of lambda by 2. A path difference of lambda by 2, as all of you have listened to a lot of lectures on path difference, a path difference of lambda by 2 will lead to what kind of interference? A destructive interference. As students have gone through a course of lectures on interference, so a path difference of lambda by 2 will lead to destructive interference. Then here from here to here is B plus lambda by 2. From P to M2 is B plus lambda. P to M3 will be again B plus 3 by 2 lambda. This is lambda by 2, lambda, 3 by 2 lambda. So the path difference between the light coming through first half period zone and from the second half period zone, they will differ by lambda by 2. From the second half period zone to third, that again differ by lambda by 2. From a third zone to fourth also, there will be difference of lambda by 2. Therefore, you will have first and 3 will interfere constructively, obviously, because lambda by 2 and 3 lambda by 2. How much is the path difference? Lambda. Whenever the path difference is lambda, there will be constructive interference. Between lambda by 2, you got here lambda B plus lambda, and then next 3 lambda by 2, between two successive zones, there will be destructive interference. On the other hand, alternate zones, first zone and third zone, they will be in phase. The two successive zones will be out of phase. Therefore, in the next slide, I will show. So, for the sake of clarity, I am showing OP is B. How do you draw OM1? This OM1 is the PM1, the magnitude of PM1 is PM1 will be B plus lambda by 2. P to M2 will be B plus lambda and so on. Okay, these things you can understand from this diagram or from this diagram. Now, the important point I want to make is the following. If a sphere is constructed, or you can construct number of spheres, with P as center, right, with P as center, you draw spheres, radii equal to B plus lambda by 2, B plus 2 into lambda by 2, then B plus 3 into lambda by 2, etc. You draw the spheres. These spheres that you draw with the P as center will give rise to the so-called half period zones or half period elements on the plane wavefront. Each zone differs from its neighbor, as I told you just now, by a phase difference of pi or a path difference of lambda by 2. A path difference of lambda by 2, all of you know, will correspond to a phase difference of pi. A phase difference of pi means what? 180 degree. 180 degree means there will be two successive zones will be opposing each other. Thus, the secondary waves starting from the point O and M1 and reaching P will have a phase difference of pi or a path difference of lambda by 2. So, I compare O with M1. The light coming from O and M1, they will differ by a path difference of lambda by 2. Here from O to P is B, from M1 to P it is B plus lambda by 2. So, a path difference of the two light beams between O to P and M1 to P, the path difference will be lambda by 2. If there is a path difference of lambda by 2, then there will be a phase difference of pi. So, the light coming from O and M1, they will interfere destructively. Okay. This is the important point. A Fresnel half period zone with respect to an actual point P is a thin annular zone of the primary wavefront in which the secondary waves from any two corresponding points of neighboring zones differ in path by lambda by 2. This is what I have shown just now from the diagram. O is the pole of the wavefront xy with reference to external point P. OP is the perpendicular to xy. All these things are known. So, in 1, 2, 3, etc., the zones, the circles that I showed, 1 refers to the first half period zone, 2, 3, etc., the respective half period zones. OM1 is the radius of the first zone, OM2 is the radius of the second zone, and so on. P is the point at which the resultant intensity is to be calculated, and you know OP is equal to B, that is what you saw in the diagram. OP is equal to B, okay. Then you have OM1 is equal to R1, OM1, right, is OM1 is R1, OM1 is what? The radius of the first circle or the first half period zone, that is our R1, OM2 is R2, OM3 is equal to R3. Now what I am going to do is, I am going to calculate the areas of the half period zone, first half period zone, second half period zone, third half period zone, and I am going to show that the areas of all the zones will be equal to one another, okay. And so, they are the half period zones. So, you have got a plane wavefront, the entire thing is a plane wavefront, the screen is a plane wavefront. This is the first half period zone, the second half period, the third, fourth and so on. What is the difference between this and this? The light coming from this half period zone and the light coming from this half period zone, they will be having a phase difference of 180 degrees or a phase difference of pi or a path difference of lambda by 2. If something like you are going to have a crust, then you will be having a trough. Then you will be having again a crust here, trough here, crust here, trough here and so on. So, the light coming from the first zone and third zone will have a path difference of lambda. So, similarly, second and fourth will have a path difference of again lambda and so on. So, light coming from alternating zones will be opposing each other. That is what I am clearly showing from this diagram. If M1 is the displacement that is caused by the light beam coming from the first half period zone, M1 will have a large magnitude. I will tell you the reason for the large magnitude later. But if M1 is the amplitude of the light that is coming through the first half period zone and reaching the point P ultimately, and M2 will be having the arrow in the opposite direction. Why should you have the arrow in the opposite direction? Because light coming from the first half period zone and the second half period zone, they will have a path difference of lambda by 2. So, if the water particle is pulled up, first thing, the second will have the opposite effect. The water particle will be pulled down. Or in other words, if the ether particle is pulled up by the light coming from the first half period zone, the ether particle will be pulled down by the light coming through the second half period zone. That is the reason why they are called half period zones. Why are they called half period? the time difference between the two successive zones will be T by 2. T by 2, T refers to 2 pi. T by 2 refers to pi. Pi refers to lambda by 2. You know, a phase difference of 2 pi corresponds to a path difference of lambda. As I told you that a path difference of lambda by 2 between two successive zones, that is the reason why there is a time difference T by 2 between two successive zones. That is the reason why they are called half period zones. So, light coming from the first half period zone is M1, if it is in this direction, then the light coming from the second half period zone will be in the opposite direction. It will be pulling down. Say plus A and plus A for constructive interference, then plus A and minus A for destructive interference. So, the direction will be opposite. So, it is destructive. Again, M3 will be in this direction. M4 will be in this direction. As I told you, the zones, the successive zones will be opposing each other. Their amplitudes will be opposite each other, whereas two zones which are 1 and 3 will be supporting each other. 1, 3, 5 and so on. Look at 1. 1 is in this direction, 3 in this direction, 5 in this direction. The alternate light coming from alternate zones will be in the opposite direction. This is up, down, and so on. Okay. Now, what is the resultant amplitude? What is the resultant intensity? I have to sum up all the amplitudes, or instead of summing up all the amplitudes, what is being done? You know, intensity is nothing but the square of the amplitude. So, I will be taking the square of the amplitudes to find the resultant intensity. A Fresnel off-period zone with respect to an actual point P is a thin annular zone of the primary wavefront in which the secondary waves from any two corresponding points by neighboring zones differ by a path lambda by 2. That is what I told you just now. So, these are the things I showed you earlier, OM1, OM2, okay, all these things you know. So, M1P is equal to B plus lambda by 2, all these things we have seen in the diagram. The area of the first half period zone will be pi into O into M1 square. OM1 is the radius, pi r square. OM1 is the radius of the first annular ring. So, it is pi into OM1 square will be M1P square minus OP square. You can look at the diagram. So, from the geometrical considerations, you know M1P is B plus lambda by 2 minus B square. So, this will be equal to pi into B lambda plus lambda square by 4. That will turn out to be pi B into lambda. The area of the first half period zone is pi B into lambda. Similarly, I will show this area of the second half period zone also will be pi B into lambda. The radius of the first half period zone is R1 is OM1 is square root of B into lambda. I will show the relationship between the radii of the various zones. The radius of the second half period zone is OM2 is square root of 2 into B into lambda. So, the radii of the different zones will be the square roots of the natural numbers. 1 into B into lambda, 2 square root of 2 into B into lambda. The radii will follow this kind of rule, but the areas of the zones will be equal to one another, pi B lambda. So, the area of the second half period zone is pi into OM2 square minus OM1 square. So, it is again pi r square. So, that will be your the area of the second half period zone is pi B lambda. The first half period zone also is pi B lambda. So, the important point to be remembered is the areas of the first, second and third, all the half period zones will be the same, pi into B into lambda. What is B? B is the distance separating the center of the plane wavefront O and the point P at which you find the resultant intensity. This is the center of the plane wavefront O, and P is the point where you find the resultant intensity. Our aim is to find the resultant intensity at the point P and to show that the resultant intensity is negligibly small. That is the reason why you have darkness in the field of view. Let me now summarize as to what we have seen in this lecture. The rectilinear propagation of light or the formation of shadows can easily be explained on the basis of Newton's theory of light, as light is assumed to travel in the form of rays. The fact that light bends around the edges of obstacles, the phenomenon of diffraction, looks like creating problems for the wave theory to explain the rectilinear propagation of light. Huygens, however, was able to explain the formation of shadows. According to wave theory, light source emits a primary wavefront and it in turn emits secondary wavefronts, and each secondary wavefront acts like point sources, and thus the disturbance advances. The plane wavefront is divided into half period zones. And the questions that we have for this lecture are: what is a primary wavefront? How does one explain the propagation of light? What are half period zones? Why are they called as half period zones? Develop the theory to find the resultant amplitude at a given point. With this, we come to the end of this lecture. Thank you.